Dear students, in today's session, I'm going to explain important points related to another important chapter, work, energy, and power. When a constant force acts on a body of mass m in a particular direction, and if the body is displaced in some other direction, and if S is the displacement of the body, and if these two vector make an angle theta, then the work done is measured by the product of the force and component of the displacement in the direction of the force. F is the force. S is the displacement. What is the component of the displacement in the direction of the force? It is S cos theta. So therefore, W is equal to F into S cos theta. So this is the expression for the work, where F is the force, S is the displacement, and theta is the angle between the force and the displacement. If theta is equal to 0 degree, then cos 0 is 1, so we get W is equal to Fs. If theta is 90 degree, cos 90 is 0, we get W is equal to 0. If theta is equal to 180 degree, cos 180 minus 1, so we get W is equal to minus Fs. That is, work done is either positive or 0 or a negative. So example for positive work done. Freely falling body. Force acts in the downward direction. Displacement is also in the downward direction. Therefore, work done by the gravitational force is a positive. Theta 90 degree. Work done is a 0. When a body moves in circular path, uniform circular motion, the force is along the radius towards the center. The displacement is along the tangent. So the angle between the force and the displacement is 90 degree. Therefore, work done is 0. So example for 0 work is work done by centripetal force is 0. When theta is 180 degree, work done is a negative. When a body is thrown upward, the displacement is in the upward direction, whereas the gravitational force acts in the downward direction. That's why work done by the gravitational force is negative, which is W is equal to minus Fs. Work done is a scalar quantity because work done is the dot product of the force and the displacement. The SI unit of the work is joule, but more important is its a dimensional formula, which is highly used to write the dimensional formula of various other quantities. So what is the dimensional formula of the work? Force mLT minus 2 into displacement, which is L. Therefore, do remember the important dimensional formula of the work, which is mL square T minus 2. Now, using these equations, we can find the work done by the static friction. We can find the work done by the kinetic friction. So you again consider an arrangement where, so we have a mass M1 over which another block M2 is placed, and a force is applied on M1, and this block get displaced through a distance. Yes, so S is the displacement of the block M1. When M1 is displaced, if there is no relative displacement between M1 and M2, that means if M2 remains at rest on M1, why it remains at rest? Because when the block M1 moves towards the right, the frictional force between M1 and M2 acts towards left. And since M2 is at rest, the kind of the frictional force which is acting between them is static friction, which is Fs. So this is the frictional force that acts on M1 because M1 tends to move towards the right. The frictional force that is acting on M2 has to be opposite of this Fs. Therefore, the frictional force on M2 is in this direction. Now, what is the displacement of M1? It is S. What is the displacement of M2? That is also equal to S. Therefore, what is the work done by frictional force on M1? On M1, the force acts in the right hand side, whereas the frictional force acts left hand side, whereas the displacement is to the right. So angle between them is 180 degree. Therefore, the work done is negative, which is the minus Fs into S. On M2, the frictional force and the displacement are in the same direction. So theta is 0, work done is a positive. Therefore, W2 is equal to plus Fs into S. So this is how we can calculate the work done by the frictional force on both the blocks. So what is the net work done? So the net work done is the sum of the work done on both the blocks, and that is equal to 0. So that's why there is no relative motion between M1 and M2. Now this is regarding the work done by static friction. How to find the work done by kinetic friction, for which you take a similar arrangement where we have a block M1 on which a force F acts in this direction. The block is get displaced by a distance S, and on this block we have another block which is M2, and when M1 is displaced, this block M2 moves backward by a distance x. So that what is the net displacement of M2? So this is S, and the block moves x distance backward. So therefore now the displacement of M2 is S minus x. It is S minus x is the net displacement of M2. And again, when the block M1 moves due to the force F, the force that acts between M1 and M2 is now not static, because there is relative motion between M1 and M2, and the force that is acting now is force of kinetic friction in a direction opposite to that of F. Similarly, due to that Fk, an exactly opposite frictional force which acts on M2 in this direction. So now what is the work done by the force of kinetic friction on M1? So on M1, the force is towards the left, displacement is towards the right, the angle between them is 180 degree. Therefore, the work done W is equal to minus Fk into S. What is the work done on M2? That is W2 is equal to, the force is Fk, the net displacement is S minus x, and both are in the same direction. So therefore, the work done is positive, which is W2 is equal to Fk into S minus X. So what is the net work? So net work done, W is equal to W1 plus W2. So when we add this, minus Fks and plus Fks will get cancelled, giving minus Fk into X. So here the net work done is not zero, as there is a relative motion between M1 and M2. So therefore, conclusion from both the diagram is that the work done by the static friction is always zero, whereas the net work done by the force of kinetic friction is not zero. So whenever force acts on a body, we can always draw the graph that shows the variation of the force acting and the displacement of the body. Force versus displacement. If the force acting on the body is constant force, then when the force is constant, the graph is a straight line parallel to the x-axis, because the force doesn't change with the displacement. So this is a graph that shows force, constant force versus displacement. If the force is a variable force, then we get a graph of any shape, but definitely not a straight line parallel to the x-axis. It can be a straight line but with a slope, or a nonlinear curve but not a straight line, because if it is a straight line parallel to the x-axis, it has to be a constant force. Now when the force is constant, and in this graph I'm going to find the area below the graph, area. So in this case, the area is the area of the rectangle, which is the length into breadth, which is the F into S. So area below Fs graph always gives work done by the force. Area below Fs graph measures the work done. Now how to find the work done if the force is variable? In such case, we have to consider a very small displacement ds, within which we have to assume that the force is constant. Then integrate the product of the constant force and the displacement, and integrating over the total displacement. Let us consider the initial displacement or initial position to be S1 and the final position to be equal to S2. So within the limit S1 to S2, we get the total work done. So therefore, if the force is variable, to find the total work done, we make use of the integration format, where force is integrated with respect to the displacement within the limits S1 to S2, where S1 stands for the initial position or the initial point where the body is placed, and S2 is the final distance that is covered. And the magnitude of this vector F dot ds can also be written as like this. F dot ds is nothing but F ds cos theta, where theta is the angle between the force and the displacement. And if the body moves along the straight line, then theta is 0, so that you'll get cos 0 is equal to 1. How to find the work in the case of a constant force? Directly you can make use of W is equal to F into S. So therefore we use the format W is equal to Fs if force is constant, and we have to make use of the integration format, because the force is not constant. So that's why to find the total work done, use the integration where the force is integrated with respect to the displacement. Now when we write this equation, we are assuming that F depends on S. So F is a function of S. Suppose if F is a function of X, then change the format of the equation or change the variable. Then you write W is equal to integration the limits x1 to x2 f dx cos theta. So depending on how that force is given, whether force is a function of x, function of r, accordingly you have to change the variable in this particular equation. We can even find the total work done if displacement is given in terms of the Cartesian coordinates. That is, W is equal to R1 to R2, that is the limit, vector F dot vector dr, where dr stands for the position vector, and F is given by fx I cap plus fyj cap plus fz k cap, where fx, fy, fz are the coefficient of or the component of the force along three different axes. So in that case, we can find the work is equal to integration of x1, x2, that is the limits for x-axis, fx into dx. Now that gives the work done by the component of the force along the x-axis. Add the net work done along the y-axis, y1 to y2, y1 to y2, fy dy, and then add this along with the work done by the force along the z-axis, which is z1 to z2, that is the limits, and then fz dz. So we use this format if the work given in terms of the Cartesian coordinates. So therefore, different formats of the equations are used. So depending on the data, we have to change the format of the equation. If the force is constant and if position vectors are given, R1 and R2 are the position vectors. For a constant force, which is F, if R1 and R2 are the position vector, this is the initial position, this is the final position. Then how to find the net work? So work done is equal to constant force, the net displacement. How do you find the displacement when vector R1 and vector R2 is given? The net displacement is R2 minus R1. So therefore it is the dot product of R2 minus R1. That gives the net displacement, and this is how we can find the work done. Now if net displacement R is given as x I cap plus y j cap plus z k cap, and if force is given with the coefficient fx I cap plus fy j cap and fz k cap, we know the value of f and r. Then with the help of the dot product of the two vectors, when the work done is given by f dot r. So how to find the dot product of the two vectors? By multiplying the coefficient of the force and the displacement, which is fx into x plus fy into y plus fz into z. So this will give the net work done when force and the displacement are given in terms of the unit vectors. So a few cases related to work done you need to remember. The first one is what is the work done in lifting a body from the surface of the earth. So surface of the earth is taken as the reference, and if the body is lifted through an height h above the ground, then the work done W is equal to m, g and h. Mass of the body, acceleration due to gravity, and the height above the ground. Now the same format is useful in few other cases where we have an inclined plane, inclined by an angle theta. H is the height of the inclined plane. L is the length of the inclined plane. And if a body which is at the base of the ground is taken along the inclined plane towards its other end. So now when this body is displaced, what is the net vertical displacement? The vertical displacement is h. Therefore, work done is equal to m, g, and h. But we want to express that in terms of L. So from the diagram, h by L is equal to sine theta. Therefore, work done is equal to m, g, L, sine theta is the format used to find the work done in displacing a body from the base of the inclined plane to the top of the inclined plane. Again, we are going to use the same format in one more case where, so we have a pendulum whose length is L, and the pendulum when taken to a side what is the work done to change the position of a pendulum, or what is the work done to shift the pendulum through an angle theta? Now, this is L, length of the pendulum. You can see the center of the bob of the pendulum is raised through an height h. So, work done is equal to mgh. And if you are able to find this h, then we'll get work done to displace the pendulum through an angle theta. So if this is L, this distance here is L cos theta, L cos theta. Therefore, the value of h is L minus L cos theta. L minus L cos theta, which is L into 1 minus cos theta, and that's the value of h. So that's why work done is equal to mg L into 1 minus cos theta. So this is how we find the work done in displacing the pendulum through an angle theta through a height h. Next, if we take a spring, when spring is compressed or elongated, so we have to do the work. So when we apply a force on the spring, the force applied and the displacement are in the same direction. Whereas the restoring force and the displacement are in opposite direction. Therefore, there are two cases which you need to remember. One, work done by the applied force is positive, which is half k x square. Whereas work done by the spring force is negative, which is minus half k x square. So these are the different cases which you need to remember. Work done in lifting the height, body through a certain height is mgh. Work done in shifting the block on the inclined plane. Work done in shifting the pendulum through an angle theta. And then work done by the spring force as well as the work done by the applied force. Capacity of the body, ability of the body to do work is called energy. So that's why the unit of energy is same as that of the work, which is a joule. But there are few practical units are used. Like in heat, we use calorie, and 1 calorie is equal to nearly 4.186 joule. The energy of the elementary particle is measured in terms of the electron volt. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Or if you want to do the reverse conversion, 1 joule is equal to 6.25 into 10 to the power 18 electron volts. So these conversions are very important, especially in chapter nuclear physics, or in radioactivity, or in atoms, chapter atoms. Then practical unit of measurement of electricity, unit of electricity is 1 kilowatt hour, which is 3.6 into 10 to the power 6 joule. So 1 kilowatt hour. Kilowatt hour is the unit of electric energy, not electric power. So these are the commonly used units, and their conversions are very important. Energy possessed by a body due to its position or configuration is called as potential energy. So work done in lifting a body from the reference point to a certain height, that is a change in position. And that work done is stored as gravitational potential energy, which is given by U is equal to mgh. In compressing or in elongating the spring, there is a change in configuration. So work done is stored as elastic potential energy in the spring, and that's given by U is equal to half k x square. You need to remember the other formats as well. So F is equal to kx. So here I can replace k as F by x. So therefore it is half Fx. You can now replace x as F by k. X as F by k, square of it. So F square by k square. So one of the k will get cancelled, and you will get this as a half F square by k. So three different formats of the potential energy, that is elastic potential energy stored in a spring, are half kx square, half fx, and then half F square by k. Potential energy and force are related. Force is a measure of negative potential energy gradient. F is equal to minus du by dx. Force is a vector. Energy is a scalar. But energy gradient is a vector quantity. So therefore, I can write this vector F is equal to minus du by dx, then I cap. So this is how we write the equation in terms of the vector form. Now, what if this force has components in three different directions? So in this, it indicates that the force acts along the x-axis only. What if the force acts in such a way that it has a x component, y component, and z component? In that case, I can measure that force is equal to gradient minus of the gradient along the x-axis minus du by dx. Now dx, dy along the y-axis minus du by dz k cap. So this is how we can find the net force. So this represent Fx here and I cap. This represent Fy, j cap, plus this represent Fz and then k cap. And if you want to find the magnitude of the force, go for the addition of the vectors, which is the root of Fx square plus Fy square plus Fz square. Now, from this relation, force and the energy, we can understand the equilibrium condition of a body. So there are basically three types of equilibrium. What do you mean by equilibrium? If du by dx is equal to 0, that is, energy gradient is 0, We know that from this equation, F is equal to minus the du by dx. When du by dx is equal to 0, F is 0. The net force is 0. When the net force is 0, the body will be in translatory equilibrium. The three types of equilibriums are stable equilibrium, unstable equilibrium, and then the neutral equilibrium. If I consider a bowl like this and with a small sphere or a small marble like this, right now it is at rest, it's an equilibrium, and if I displace it, it comes back to the same position. That is called stable equilibrium. In stable equilibrium, once the body is displaced, it comes back to the same position. You take the inverse, reverse the ball, and then place the marble over it. It's in equilibrium, and now if I displace it, it will not come back to the same point. It will attain a new equilibrium, and that's called unstable equilibrium. I'm going to consider a horizontal surface where we have the same marble which is placed, and now it's in equilibrium, and if I displace it, it will attain a new equilibrium which is called the neutral equilibrium. And in stable equilibrium, the energy is a minimum. That can be even negative also. I'll write U minimum. And in unstable equilibrium, the energy is a maximum. Whereas in neutral equilibrium, the energy is constant. And this we can even understand in terms of the graph. So if I draw energy U versus X graph, U versus X. And if we get a nonlinear graph, I will draw a tangent to the graph, and then I'm going to measure the slope. The slope here is a du by dx. Du by dx. And that du by dx is nothing but minus f. So slope of energy versus x graph gives negative of the force. Du by dx is equal to minus f. Now if x increases, and if u also increases, see here, if x increases and if u also increases, then both are positive. The force becomes a negative, F is a negative. And when force is negative, the nature of the force is attractive. That means the body tends to move towards each other. We can very easily understand this from the two charges. Energy U is directly proportional to the product of the two charges. Energy U is directly proportional to the product of the two charges. If Q1 is positive and if Q2 is negative, then the product will give you energy negative. U is a negative. And when U is a negative, we know that the force between them, just now I've told you, is attractive. Not only that, in this case, if X increases, U also increases. That's why the force between two unlike charges is attractive in nature. Why do two charges attract can be explained very easily using the potential energy between the two charges. And now if X increases and if U decreases, with increase in X, if U decreases, then based on this equation, increase in X decreases U, means that du becomes a negative, So force becomes positive. F becomes positive. And when the force is positive, the nature of the force is repulsive. And if we take two like charges, plus plus, between two like charges, if distance between the two like charges is increased, their potential energy decreases. That's why the nature of the force is repulsive between two like charges. So force is always related to the potential energy. To understand the three types of the equilibrium, the stable, unstable, and neutral equilibrium. So sometimes they'll give the graph related to the potential energy versus distance, and then will be asked to find the stable, unstable, and neutral equilibrium. So in this graph, you get to see at point A, the potential energy is minimum. That means the body is in stable equilibrium at A. At B, you get to see that the potential energy is maximum. So that's why the body is in unstable equilibrium. And at C, you can find the energy is constant. That means the body is in neutral equilibrium. The energy possessed by a body due to its motion is called kinetic energy, which depends on the mass of the body and its square of the velocity. K is equal to half mv square. In this equation, m into v is momentum. Therefore, you can even write half p of v. If I multiply by m and then divide by m, then I'll get half m square v square by m. That is half p square by m. So these are the different formats of the kinetic energy. You can even write the formula for momentum out of it. That's P is equal to 2k by v, 2k by v, or P is equal to root of 2mk. And based on this, various graphs are possible. K versus V. K versus V, or it can be even P. So K is equal to half mv square is of the format y is equal to ax square. Even K is equal to P square by 2m is also of the same format. So that's why K versus V or K versus P is a parabola symmetric about the y-axis. Now, what is the nature of the graph for P versus root K? P versus root K. So here I can write P is equal to root 2m and then root K. That is, y is equal to mx format. So it is a straight line passing through the origin. Now, how to relate P versus 1 by root K? P versus 1 by root K. Now this we can write the same equation. I can write it like this. It's a root of 2m and then 1 by a root K like this. P is equal to root of 2m and that root K I can write is 1 by root K. So now this equation is of the format y is equal to a constant here by x, or xy is a constant. So since y is inversely proportional to x, it's a nonlinear graph, or you can even write an hyperbola like this. So this is a p versus 1 by root k, because it's of the format y is inversely proportional to x, or x is inversely proportional to y. We get similar equation in Boyle's law where PV is equal to constant. So therefore, P versus V is a similar graph. P versus V is a graph which is a nonlinear, or it's called as the hyperbola. So what is the relation between the work and the energy? So that we can relate in an important theorem called as work energy theorem. So according to the work energy theorem, the net work done, total work done, is equal to the change in the kinetic energy. Now that, when we say total work done, that includes work done due to the external forces, external, plus work done due to the non-inertial frame of references, that is non-conservative force, work done by the conservative force is equal to delta K. So this is how we write all forces, other forces, external forces, work done due to the non-conservative and the conservative forces. Now what do you mean by conservative and the non-conservative forces? If the work done by the force is independent of the path, then it is called conservative force. Example is gravitational force, electrostatic force. And then work done by non-conservative force means, or a non-conservative force is one in which the work done depends on the path. All opposing forces are non-conservative forces. Frictional force, viscous force. So all the forces are to be included, and that gives the net work done. So total work done is equal to the change in kinetic energy. So we can use this work energy theorem to solve a lot of numericals where, in the case of kinetic energy, I can write W is equal to half m Vf square minus Vi square, where Vf is the final velocity, Vi is the initial velocity. In the case of potential energy, I can write mg into h2 minus h1. If a body which is already at a height h1 is raised further to an height h2, then what is the work done in shifting from point A to point B? So W is equal to mg into h2 minus h. We can even use this W is equal to half k x1 square minus x2 square. What is the work done in stretching the spring from one position to a new position? So work done is equal to change in elastic potential energy. Work done is equal to change in gravitational potential energy. Work done is equal to change in kinetic energy. So for any form of energy, this work energy theorem holds good. And some of the numericals can be solved using the law of conservation of energy, where the total energy of the system remains constant. And in one such a case, total energy of a freely falling body is used in a number of numericals. So if there is a body at a certain height, capital H, if it is allowed to fall, then the total energy remains constant throughout the motion. When it is at a height h, the potential energy is mgh, mg capital H, and there is no kinetic energy. So that's why that itself is the total energy. So total energy E, I'm going to write, is equal to mgh. And I can use this mg capital H at any point in its path. So what is the total energy at this point? It is mgh. What is the total energy at this point? It is mgh. And in such numerical, they'll give two data. One, what is the potential energy at a particular height? Or what is the potential energy and the kinetic energy after traveling certain time? If they ask you to find the potential energy at a particular point A, after traveling certain distance, let us consider x. Then, right now, the body is at a height h minus x. So we can find the potential energy at this point, which is equal to mg into h minus x. And once we get the potential energy, it's very easy to calculate the kinetic energy. It is equal to total energy minus the potential energy. So always find the total energy at the beginning, and then you can make use of to find the other forms of energy. Suppose if they give time instead of the height, they give the body reaches a particular point in a certain time. Then find velocity in reaching that point using v is equal to gt. And once you get the velocity, find the kinetic energy using half mv square. And we know the total energy, we know the kinetic energy. So now you can find the potential energy is equal to total energy minus kinetic energy. So therefore, this is the reason why that total energy is useful in finding the other forms of energies. So I'm going to apply this in three different diagrams. So we have a frame and then a spring. We have a block M, and then here we have a spring attached. And again a sphere at a height h, and then a spring which is connected to a rigid support. So in the first case, if I consider a block which is at a height h, if it is allowed to fall, then what is the maximum compression in the spring? When the block falls on this platform, it's get compressed. Let us consider this frame is get compressed through a distance x, so that the block falls through a total height of h plus x, so that the block comes to a rest at this point. When the block is at a height, the energy possessed by it is potential energy. So what is the total distance covered by the block in falling? It is a h plus x. And if I multiply by mg, I'll get the total change in its potential energy. Potential energy becomes 0 because the block comes to rest once the spring is get compressed to a maximum value which is equal to x. And now this potential energy is completely converted into elastic potential energy in the spring. So that's why this is mg h plus x is equal to half k x square. And using this, we can find the value of x. And we have used the decrease in potential energy is equal to the gain in elastic potential energy. That is one form of energy is converted into the other form of energy. That means we have used the law of conservation of energy. So here we have a block M which moves with a velocity v, and on a smooth surface. And when this block moves with the velocity, it possesses kinetic energy, which is half m v square. And when it collides with the spring is get compressed to a distance x. So therefore, half mv square is equal to half k x square. So kinetic energy is converted into elastic potential energy. In this diagram, the sphere is at a height h, and when it slides and then hits the spring is get compressed. So here, even though it's in motion, the total energy I can calculate as a mgh, that's equal to half kx square. That is potential energy, gravitational potential energy is completely converted into elastic potential energy. And another concept which is very important in this particular chapter is collision. So when a body changes the path of the other, or if the two bodies physically collide each other, then the law of conservation of energy as well as law of conservation of momentum is applicable. When we apply these two laws, if the total linear momentum, if it is conserved, and along with this, even if the kinetic energy is also conserved, then such type of collision is called as elastic collision. So elastic collision is one in which the momentum, linear momentum is conserved, even the kinetic energy is also conserved. Total energy is anyways conserved in all type of collision. And if I consider two body system, when the momentum is conserved, we can make use of the law of conservation of momentum, which is m1u1 plus m2u2 is equal to m1v1 plus m2 of v2. This is based on the law of conservation of momentum. Kinetic energy is also conserved. So half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So this is the total energy before the collision, and this is equal to the total energy after the collision. And related to collision, we can measure a constant called as coefficient of restitution, which is denoted by E, and that is equal to the ratio of the relative velocity after the collision to the relative velocity before the collision. V1 minus V2 is equal to U2 minus V1. A ratio of relative velocity after collision to the relative velocity before the collision. A perfectly elastic collision is one in which the value of E is equal to 1. That's called perfectly elastic collision. And when E is equal to 1, we can always use V1 minus V2 is equal to U2 minus U1, because E is 1. So V1 minus V2 is equal to U2 minus U1 is always applicable for a perfectly elastic collision. Or even if they give just elastic collision, still E is equal to 1. Now, what is the velocity of the two bodies after the elastic collision. So we have two equations for it, which is again very important. And velocity of the two bodies after the collision is given by v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2 m2 u2 by m1 plus m2. So that's the velocity of the first body after elastic collision. Similarly, the value of v2 is equal to, it is m2 minus m1 by m1 plus m2 into u2 plus 2 m1 u1 by m1 plus m2. Now, out of these, we have three special cases which you need to remember. And the case one is if the masses of two bodies are equal, if m1 is equal to m2. And when m1 is equal to m2, velocities of the two bodies are interchanged after the collision. That is, v1 becomes equal to u2 and v2 becomes equal to u1. Their velocities are interchanged, and this is applicable only if their masses are equal. So if m1 is equal to m2, and if you substitute, you will get this particular condition. The case number two, second case. If m1 is much lesser than m2, that means a very light body collides with a heavier body which is at rest, then the velocity of the first body is v1 is it will remain almost the same, but it's get reversed. That means v1 is equal to minus u1. That means its velocity is the same as the previous value. That means if it moves with the 10 meter per second, it still remains 10 meter per second, but it moves in the opposite direction. Whereas the heavier body continues to remain at rest. v2 becomes 0. And this happens only if a lighter body collides with a heavier body at rest. And the third and the last case, that is, if m1 is much greater than m2, that means if a heavier body collides with a lighter body which is again at rest. If a heavier body m1 collides with a lighter body which is at rest, so v2 is 0, then velocity of the first body continues to remain same, which remains same u1, whereas the velocity of the lighter body becomes double the initial velocity of the heavier body. So v1 will continues to remain as u1 only, which velocity remains the same, but velocity of the lighter body will be double the initial velocity of the first body. So again, if you remember these cases, some of the numericals can be very easily attempted, but do remember this general expression, which is final velocity of the two bodies in elastic collision. Now, what is inelastic collision? An inelastic collision is one in which momentum is conserved. That's m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. But kinetic energy is not conserved. That means some form of energy is converted into the other form. There will be some loss of energy takes place. That can be due to the friction, or that can be due to the non-conservative forces, but there will be some loss of energy takes place. So that is the reason why the total energy before the collision, that's half m1 v1 square plus half m2 v2 square. This is the total energy before the collision, is always greater than the total energy after the collision. Half m1, so this is half m1 u1 square plus half m2 u2 square is greater than half m1 v1 square plus half m2 v2 square. So total initial energy is greater. That's why you can always find the loss of energy, delta K. That is equal to total energy before the collision, which is half m1 u1 square plus half m2 u2 square minus half m1 v1 square plus half m2 v2 square. If it is one-dimensional head-on collision, that means the two bodies are moving along the straight line before and after collision. Then the loss of energy is given by the formula, which is important. Delta K is equal to half m1 m2 by m1 plus m2 into u1 minus u2 the whole square. So this is the loss of kinetic energy in the case of one-dimensional head-on inelastic collision. A perfectly inelastic collision is one in which the two bodies, they stick together after the collision. If V1 is equal to V2, final velocity is the same. That means both the bodies, they move together. So such inelastic collision is called as a perfectly inelastic collision, for which the coefficient of restitution is 0. E is equal to 0. When a rubber ball is dropped from a certain height, h1. So this is the height from which it is dropped, h1. So it strikes the ground with a velocity v1 in the downward direction. Now once it strikes the floor, there will be deformation of the rubber ball takes place. So some form of energy is lost in deforming the ball, and due to friction, a very less amount of energy is lost in the form of heat. So because of the loss of energy, the ball rebounces back in the upward direction with a lesser velocity, which is v2. So v2 is lesser than v1, due to which it rises to an height h2, which is lesser than h1. So h2 is lesser than h1. So in this case, we can measure the coefficient of restitution, which is E is equal to, it's V2 by V1. But since V is proportional to root of H, it is also equal to root of H2 by H1. So ratio of the velocity or the ratio of the heights are used in finding the coefficient of restitution in the case of inelastic collision, because here there is a loss of energy takes place once the ball strikes the ground. When work is done by a body, the rate at which the work is done is measured as power. So power is equal to work done by the time taken. Work is measured in joule, time is measured in seconds. So therefore, joule per second is measured in terms of watt. So 1 watt is equal to 1 joule per 1 second. So very easy to write the dimension formula, which is ml square t minus 2 by t, that gives ml square t minus 3. If the work is done by a variable force, the average power consumed, which is equal to the net work done, that is delta W by delta T. So net work done by the time taken to do that work gives the average power. And if you want to find the instantaneous power, then we have to differentiate work with respect to time. dW by dt. It is the limit of the average power when the time interval tends to 0, gives the instantaneous power. P is equal to W by. Power is also a measure of the dot product of the force and velocity. P is equal to F dot V. That is also equal to F V cos theta. And if I draw a graph of F versus V, F versus V, the area below FV graph, the area below FV graph gives the power that is consumed or the power of the agent. Similarly, the graph of W versus T, W into T, that is a work versus time. And if I find the slope of it, the slope of W versus T, that's a dW by dt, that gives the power. So FV graph, area of the FV graph gives the power, whereas slope of work versus time graph gives the power. In the case of engine or the motor, we can always calculate the efficiency of the device. Efficiency symbol used is eta. That is also equal to the ratio of the output power to the input power. Output power is always lesser than the input power because the power that is supplied to the device will be lost in various forms. So efficiency of the device is always lesser than 1. If efficiency is 0.8, then in terms of the percentage, it is equal to 80%. Now what that signifies is 20% of the power is lost in various other forms. And if eta is equal to 1, we consider that device as ideal. So we have ideal heat engine, ideal motor, ideal transformer, for which we consider efficiency equal to 1. So these are the important points in this lesson. Concentrate on the energy concept, work energy theorem, highly useful concept, and it is used in a number of numericals, and practice more questions on these concepts, and it's again one of the important chapter of mechanics. Thank you.